Hello, my dear students. Welcome back to Dr. Maran's Chemistry Academy. So, we're going to continue with the STPM SAM2 chemistry questions. As you all can see, this is a continuation from where we left from the previous session, right? So, I have discussed 3 MCQ questions. Now, we're going to continue with the 4th question. So, let's look at the 4th question now. Methane is produced from the following reaction as represented. You can see carbon monoxide reacted with 3 mole of hydrogen gas to form 1 mole of methane and 1 mole of water. So let's look at the question. In an experiment, 0.33 mole of carbon monoxide and 1.0 mole of hydrogen are mixed in a 2.0 decimeter cube of enclosed flask at 550 degrees Celsius. When the system achieved equilibrium, 0.9 mole of the hydrogen gas reacted. What is the equilibrium constant Kc for the forward reaction, right? So we can see that the forward reaction as given here, and there are 4 options. So this is the MCQ questions that we're going to tackle. So how to do this question, and it's related to Kc, equilibrium constant. So the first step that we're going to do is, as usual, you can actually form a ICE table, or ICE table. So what we're going to do, we're going to write the equation, carbon monoxide, and we have 3 mole of hydrogen gas as represented here, and then we have 1 mole of methane and water, right? So now what we're going to do is we're going to find the initial mole. Okay, we need to know the initial and we need to know the dissociation and equilibrium, right? So the initial mole for carbon monoxide is 0.33. Okay, so please mark it clearly in the table, and the initial mole of hydrogen gas is 1.0. Alright, and obviously initially for methane and water will be 0, right? Because it is not yet dissociated. Now, so as we all know, it is represented, during the dissociation, it is represented by negative alpha, because this is 3 mole, so negative 3 alpha. This is positive alpha, positive alpha. Alright, so what happened at equilibrium? Right, at equilibrium, alright, when the equilibrium is established or achieved, we're going to calculate what is the new equilibrium that has been achieved. So what we can see here is 0.9 mole of the hydrogen reacted. So 0.9 mole. So 1.0 from the initial, we're going to minus 0.9, which is 0.1 mole, right, has been reacted. So 0.9 mole has been reacted. So what we can see here is 1 mole of carbon monoxide to hydrogen gas, 3 mole of hydrogen gas, right? And 0.9 mole has been reacted. So what is the number of mole of carbon monoxide? So we got to take 0.9 divided by 3. So here we're going to get 0.3 mole, right? So what we can see here is 0.3 mole of carbon monoxide has been reacted. So reacted, what we're going to do is we take the 0.33 mole minus 0.3 mole, right? So what we're going to get here is we get 0.03 mole that has been reacted, right? That has been reacted. So what we can see here is we already find the equilibrium number of moles for carbon monoxide and hydrogen for the reactant part. What about the product side? Okay, for product side, you have to understand that initially it is 0 because it is not being dissociated. Once the equilibrium is established, what we need to do is we know that the number of moles is 1 and 1. So the number of moles that has been reacted is 0.9 for hydrogen, and we divide by 3, right? Because it is 1 mole. So the number of mole of carbon, methane and also water that has been dissociated will be 0.3 and 0.3. So this is the final number of moles that has been dissociated. Now, what students mistakes? Most of the time, students tend to do these mistakes. and they tend to forget that they need to divide by the volume. Why volume? Because we are, as long as Kc, the equilibrium constant, is concerned, don't forget that you need to find the concentration, right? So what is the expression for Kc? What we will do, we will take the concentration of methane, concentration of water, okay, divide by the reactant, which is the concentration of carbon monoxide and concentration of hydrogen, express Q. Because as I mentioned earlier in my previous tutorial class, I also did mention that any stoichiometrical coefficient value, all right, we need to raise it to the power of that particular reactant or product. So here what you can see, 3 as a coefficient value, right? This is a stoichiometrical equation. So 3 will be raised as a power. So what we're going to do, we're going to raise as a power, and we're going to use this formula to calculate our Kc. So now how to find? We already have all the mole. Now we need to find the dmq, because the concentration unit is mole per dmq. We already found the mole. So where is the dmq? Dmq is already mentioned here earlier in the question, 2 dmq. So what we're going to do, we're going to find the concentration for each. So first, for carbon monoxide, we're going to take 0.03 mole divided by 2. Alright, this is for the concentration of carbon monoxide, and concentration for hydrogen will be, hydrogen is here, we take 0.1 mole divided by 2, and concentration for methane, alright, methane, which is 0.3 divided by 2. Okay, 2 is the volume, the dmq, okay, that given in the exam. And your water, the water mole is same as methane, okay, because there are shared equally 1 mole. So we're going to find all this, right? We're going to find all this. So if you look at the let me use my calculator to find all the values. Okay. So I get 0.015 mole per dmq. Okay, 0.015 mole per dmq. And the next one is 0.055. Next one is 0.15. So I'm getting 0.15. So it's same as this, right? So it's same as this. So I already got all the concentration, right? All the concentration of the product and reactant. So what I'm going to do next, the final step is I'm going to substitute into the expression, the formula. So the methane, the concentration of methane will be, we take the 0.15 multiplied by the concentration of water, which is 0.15 as well, divided by the concentration of carbon monoxide, which is 0.015, and multiply by the concentration of hydrogen, which is 0.05. And don't forget, there is a stoichiometrical coefficient value which is raised to the power. So I'm going to put Q here. So I'm going to find this answer finally. Give me a second. So I'm getting 12,000, right? So this 12,000, let's look at the answer option. 12,000 they express in this form, so it will be 1.2 1.2 times 10 to the power of 4 dm cube per mole cube. Dm cube, sorry, not dm cube, dm to the power of 6 per mole square. Right? So what we can see, the answer is clearly is B. Right? So B is the answer for this question. So I believe it is very meaningful and beneficial to all of you. So how, if let's say it's related to Kc or Kp, for Kp is an equilibrium constant for the pressure gas, right? Even though it is all a gas, but as you know, we can also find Kc for this type of question. All right, so it is not limited to only Kp, but we can find Kc. But for Kp is only applicable for gaseous related. All right, not for any aqueous. So Kp, we're going to use the Dalton's law of partial pressure. It's the principles is same. Okay, we're going to use the ice table, but it's going to be more like we're going to apply the Dalton's law of partial pressure. All right, so I will see you in the next session with a more interesting topic. Of course, I'm doing this bit by bit because I need a lot more space, okay, to record this video so that all the students could beneficial, all right, from this STPM exam question discussion. So I will see you in the next tutorial session. Please don't forget to subscribe to my channel and also to follow my TikTok channels, right? Thank you.